Hey students, welcome to lecture number 6 of multiple zeta values and modular forms. So today we want to continue to talk about the algebraic setup of our objects. So here in the overview, last time we started with section number 2, and in this section we talked about iterated integral expressions of multiple zeta values, and we talked about the multiple polylogarithm, and we saw that these products of multiple zeta values can be written by using the Schaffer and Schaffer product, and this we described by defining the Schaffer and Schaffer product on this formal space which we denoted by H0, and then we said that this zeta can be seen as an algebra homomorphism from this space to the space of multiple zeta values. And because this was an algebra homomorphism with respect to these two products, this Schaffer and Schaffer, we obtained linear relations among these objects. So today we want to generalize this algebraic setup by introducing so-called quasi-shuffle algebras. And the reason for this is that we also have this object G, which does not satisfy the Schaffer or the Schaffer product. But we already saw here in section 1.4 an example when we multiply two of these Q series G in depth 1, then we could write them as a linear combination of small g's, which looked quite similar to the Schaffer product, but we had some extra terms. And to describe this in some algebraic setup, we need to introduce these quasi-shuffle algebras. But first, let me do a small review. So last time we introduced this space H, which was just a non-commutative polynomial ring in two variables x and y. And there we considered a subspace H1, which were the words. So by a word we meant a monomial in this space in x and y, and the space H1 were the words ending in y. And this was also given as a span of these words zk. So we defined for a k greater or equal to 1, we said that zk is x, k minus 1 times and y. And then for an index, so if k is an index k1, kr, then this zk of an index is just zk1 up to zkr. And then the elements in this H1 correspond to this zk for an arbitrary index k. And inside this space we had the space H0, which was a span by all zk's, where this k was an admissible index. And in the language of these x and y, this just meant these were the span of all words starting in x and ending in y. And then on these spaces we defined these products. So first we defined the Schaffer product, denoted by this on this space H, and this was defined recursively by this formula here. So first, if we take the Schaffer product with the empty word, then that didn't do anything. But if we have a word starting in the letter A1 and a word starting in the letter A2, then you shuffled these words together and got the Schaffer product. And then we also defined the Schaffer product, but this we defined on the space H1, because for this definition we needed these letters zk, and this was defined in a similar way, except that there's some extra term here. And now instead of taking these letters x and y, we take these letters zi and zj. And then we saw that we get an algebra. So for the Schaffer product we got this what we denoted by H shuffle, and this subspace H1 is also closed under the Schaffer product, so we had a subalgebra here, and also this H0 was closed under this. And also for the Schaffer, so this H1 was algebra with respect to the Schaffer product, and the H0 was a subalgebra. And so what we want to do now is we want to generalize this idea here, because already here you see that they're quite similar, and both of them will be an example of a so-called quasi-shuffle algebra. And so to define this, we will replace the set of letters which were in this case x and y, and in this case we had for each natural number a letter zi. So we will replace this by an arbitrary set a, and then we will define a product which looks quite similar to this, but we will replace this thing here. So this, we started with 2 letters here, and here we got a new letter by summing the indices here, but we will generalize this by saying that we have some product on the space of letters. Okay, so let's do this. So in this section by k, we always denote a field which contains q, and actually in the video today k will always be q, so all the examples we do will basically just the case q, and a will be a countable set, and this we will call the set of letters. And now we assume that we have some commutative and associative product on this a, and more precisely we are interested in the k vector space spanned by these elements in a. And taking this product and then extending this bilinear to this space Ka, we get that this space Ka with this diamond is a non-unital K algebra, which we will denote the algebra of letters. So now let's see what this means in the example we did before. So first example is, so for example, we can take the set A to be just 2 elements, x and y, and then we can define the diamond of 2 elements a and b in this set to be just 0 for all a and b in A. So maybe this is not the most interesting case, but this will always give a non-unital K algebra like this. But maybe more interesting case, if we take A to be the set Z1, Z2, Z3. So now these Z are just formal variables, so they don't have a connection to this x and y. And now we can define this diamond product of Zi and Zj to be Zi plus j. And so with this example, so the ultimate goal will be to define now this what we'll call a quasi-shuffle product, and the idea is that this should generalize this picture here before. And for these two, the algebra of letters is given by these 2 examples here. So this algebra of letters here, so this, let's call it AZ. So this algebra AZ with this product here given by this, this is basically just the polynomial ring. So in these cases, let's also say k is q. So in this case, you can check that this is just isomorphic to this space here as a q algebra by sending zk to xk, and this will be the algebra of letters, which will give us later this Schaffer product. So, but now let's actually define what we mean by this quasi-shuffle product. So this is the definition here. So let's assume we have the setup as before. So we have some countable set A, and then on this space, on this vector space generated by A, we have this diamond product. So we have an algebra of letters, and then we define the quasi-shuffle product, which we denote now by this star and diamond. So this depends now on this diamond, and this we will define on this space here, and this is the non-commutative polynomial ring in elements in A with coefficients in K, and you should think of this as being just words in the letters A, or more precisely K linear combination of words in letters in A. And we define this product like this. So we say the empty word, which is an element here, taking the quasi-shuffle product with any word, will be just this word. And then if I take the quasi-shuffle product of two words where the first word starts with A and the second with B, then the definition is exactly as before. We take first A outside, then B. But here is now the new part. So here we take this product in the space Ka. So this will again give a linear combination of letters. And these products here, so here and this, so this is just a concatenation in this Ka. So this is just a non-commutative multiplication in this space. So you just put the letter in front. So this is well defined because this is just this is a product on this Ka. So this gives a linear combination of letters, and this is a word. So we can just attach the word in front. And then the statement is that this space equipped with this product becomes a commutative K algebra. And this will then be called, so this is a quasi-shuffle algebra. And you should also think of this as being the algebra of words. In the letters A. So we have two algebras, the algebra of letters and the algebra of words. And so the first thing we want to show is this lemma here. And we will start with an example. But first let's go through this the statement of this lemma here. So R is now an arbitrary K algebra, and we assume that we have algebra homomorphism for each natural number m. We have an algebra homomorphism small fm from the algebra of letters. So here it's really algebra of letters. In this algebra R. And then we can construct a new map now from the space of words. So here's words. And we will denote this by f, capital Fm, for each natural number m. And this we will define, so we define it for a word and then extend it linearly to the whole space. So if I have a word like this in R letters, A1 to AR, so this is a word in this space of words, then we define this Fm of this word to be this finite sum. So this is really an element in this K algebra R, where we apply Fm1 to the first letter, Fm2 to the second letter, and Fmr to the last letter, AR. And we multiply, so the multiplication here again is just the concatenation so in this case, the multiplication here is of course just the multiplication of elements in R. So this is an element in R, and this multiplication here is just the multiplication of elements in R, which is the K algebra. So, and then the statement is, also we set the image of the empty word to 1, and then the statement is that we get an algebra homomorphism from the algebra of words. So here this is a quasi-shuffle algebra of words to R. So again, having a family of algebra homomorphisms from the algebra of letters to R, we can construct an algebra homomorphism from the algebra of words to R. So and what does this have to do with multiple zeta values? So let's do again the example we saw before, namely let's take again AZ to be Z1, Z2, and so on. And again we take the the diamond which gives the Schaffer product. So we have this. So now let's define a family of algebra homomorphism, Fm, from this space here to R. And R in our case, let's say it's Q. So what we can do is, I want to define Fm, and the input of Fm should be an element, a linear combination of these letters, but it's enough to say what I do with one letter. And this I want to send to an element in Q, depending on m. And what I do is I just take 1 over m to the k. And then you can easily see that if I do this, then this is really an algebra homomorphism to the rational numbers, because Fm of that j diamond that I, well, this is Fm of that j plus I, and this is 1 over m to the k, but this is the same as Fm of that j times Fm. Oops. Of course, this k is now j plus I, and this is the same as Fm zj, because this is 1 over m to the j, and this is 1 over m to the I. So this gives an example of an algebra homomorphism from the algebra of letters to the rational numbers. And what is the capital F in this example? So, well, if you, for word W, so let's say the word W, so it should be some word in this alphabet here, so it will be some zk1 up to zkr. And what is this fmw? Well, it's an ordered sum here. And then I plug in fm1 of the first letter, so fm1 of this, but this is just 1 over m1 to the k1 multiplied now in q times up to mr to the kr. So you see that this is just what we denoted before by zeta m k1 to kr. And then the statement of this lemma in this example here is that that we get an algebra homomorphism from this quasi-shuffle algebra. So in this case, this quasi-shuffle algebra is Q A Z with the Schaffer product corresponding coming from this diamond here. But this is actually just the same as what we denoted before as H1 Schaffer. And then the statement is that we get an algebra homomorphism from this to Q by sending a word zk1 up to zkr to this truncated multiple zeta value. And this statement we already saw before, even though we didn't prove this, but we will now prove this statement here in general form. And I hope this example makes clear what the idea behind this construction is, because in this simple case here we get exactly our object back, these multiple zeta values. And of course, so the idea why we generalize is because it's this small f in the case, for example, for our Q series G will be given by these rational functions with these Eulerian polynomials. Okay, but now let's prove this lemma. So what do we need to show? Well, we need to show that that the product of these two f's for words W and V, so this is now the product in R, that this equals Fm of the quasi-shuffle product. And So this, so let's remove this here for a second. This we will do induction by induction on m. So for m equals 1, this is quite simple, because if m is equal to 1, then there's not much happening here, because if m is 1, no matter what r is, this will always be an empty sum, so this will always be 0, except for the case when this w is actually an empty word. So if m is 1 and these are non-empty, then the equality is just 0 times 0 equals 0. But if one of them is empty, then this by definition is just 1, and here by definition this is just, so let's assume w is empty, then this is just 1, and here this product is just v, so this statement also becomes trivial. So in this case, when one is empty, this is also clear. And of course, when both are empty, this is also clear. But now, let's do the induction step. And for this, we first need to notice something, namely, so if I have a word, w, which starts with some letter a, and the rest is w prime, then fm of w is just given by taking this sum here, where I take fm of a times capital F small m of w prime. So this is just by definition of this capital F. So if you would also write this out, you see that you get exactly this ordered sum here. So now let's assume we have two words like this. So I have a word w starting with a and a word v starting with b. And I now want to calculate the product of fmw and fmv. By definition, this is just this because of this equality here. So for both of them we can just make this sum where we put this first letter here in front. And now we play this usual game, which we did several times for this Schaffer product, by taking the product of these sums and then considering all different cases where, so this small m here could be larger than this n, this could be larger than this m, and they could be the same. So these three cases we have here of this product. And then we can rewrite it like, so the first sum gives this part here. So when m is greater than n, then we get this here. And if n is greater than m, we get this part here. And now in the case if m equals n, we get this sum here, where all of them are n. And now, because this small f is an algebra homomorphism for each n with respect to this diamond product, this part here is just given by fm of this single letter a diamond b, or more precisely of this linear combination of letters. And here we can just use the induction hypothesis, because this m here is strictly smaller than m, and we do induction on capital M here. So this is also why we can use the induction hypothesis here to write these parts here as a product. And then in the end you see that we get the recursive formula of the definition of the quasi-shuffle product. And therefore we get that this equals this. Okay, so now we want to do some examples and then use this lemma. So here we already have one example with these multiple zeta values. So this lemma in particular shows that the space of multiple zeta values, the Q vector space, is an algebra, because this makes sense for these truncated and sending m to infinity. We get this statement. We get this statement here for multiple zeta values, but we also want to apply this lemma to our space spanned by these Q series G. So we will need to make we need to define this diamond and this small f for this case too. But first, let's do some easy observation. And so now we want to talk about subalgebras and examples. So, but first, this observation here, namely, if I have the set of letters A and I have a subset B, such that this space spanned by B is closed under this diamond product, meaning we get a subalgebra of letters, of the subalgebra of letters here, then the statement is that the space of words, where we just use letters in B, is also a subalgebra of the space of the algebra of words, where we use all letters in A. And this is quite simple to see by the definition of the quasi-shuffle product. So, assuming the space of letters in B are closed under this diamond product, and I now start with words in B, this in particular means that A and B are in B, and therefore, so if A and B are in B, then also A diamond B is in the vector space generated by B. And therefore this is a linear combination of letters in B, and then the whole element, so the whole side here is in the algebra of words in letters of B. Okay, so clearly if we have something like this, we can construct subalgebras. So similar as before, we had algebra homomorphism from this algebra of letters, which gave us algebra homomorphisms of the algebra of words. We now have the statement that subalgebras of letters also give subalgebras of words. Okay, so now let's do some examples for quasi-shuffle algebras. And in this video we will just do 3 examples, but you can also find more examples in the lecture notes. So the first example I already mentioned is the Schaffer product. So in the case for any A, we can define, so if I have some letters A and B, we can always define the boring product, which just sends everything to 0. And then the quasi-shuffle algebra product of this, we will just denote by this shuffle. And we saw before the example when A is xy, and then in this case so we also saw we took the case k equals q, so in this case this quasi-shuffle product, so this we denote shuffle, this was basically just h with the shuffle product. So this is actually an equality here. But we will also use this shuffle product on not just this alphabet, but also on this alphabet AZ with Z1, Z2 and so on. And this is sometimes also called the index shuffle, to distinguish between this shuffle here and the other shuffle. But maybe more interesting is this one here now. So the shuffle product, so again we take the alphabet AZ, Z1, Z2 and so on. The diamond we already saw a few times today is given by this. And then this quasi-shuffle product we just denote by this. And so we had so again we had this example here. that this is basically just H1 with the Schaffer product. And we also had these algebra homomorphisms Fm from this to Q by sending, from the space of letters 1 over m to the k, and then this Fm was given by this zeta m. But now let's consider subalgebras of this. So let's define AZ, for example, greater or equal to 2 to be AZ without Z1, and AZ even to be Z2, Z4, Z6, and so on. And clearly, if I take this diamond product for elements, for example here, so meaning I and j are greater or equal to 2, then of course also I plus j is greater or equal to 2. So this gives a subalgebra of letters. So in other words, for example, AZ greater or equal to 2 with the diamond product is a subalgebra of Q. Well, here I don't need to take Q, it also makes sense for an arbitrary K, but let's do it like this. But also the space of even letters is a subalgebra, because if I add two even numbers, it's again an even number. So these are subalgebras, and then by the proposition before, we get subalgebras of the quasi-shuffle algebra. And this also gives then subalgebras of the space of multiple zeta waves, which we can define like this, for example. So here you see that the span of multiple zeta waves where the entries are greater or equal to 2, we denote by z greater or equal to 2, and the space z even is the space spanned by all multiple zeta waves where the entries are even, and from what we did now, we get that, maybe let's do it like this, we get algebra homomorphisms. So the statement basically is that we get algebra homomorphisms here from the algebra. So we want the A greater or equal to 2 that with the Schaffer product we get an algebra homomorphism to this space, and we also get an algebra homomorphism A even to this space. So in particular, these spaces are closed under multiplication, which follows from this proposition we did before, from this lemma here. So from this lemma, and together with this statement here, we get that these two spaces are subalgebras of the space of multiple zeta values. So we see that z greater or equal to 2 is a subalgebra of the space of multiple zeta values, and here we also have the space of these even multiple zeta values, which is a subalgebra of this. And actually what we know, which is a non-trivial result, is that here this is not really just a subalgebra, it's really the same, which follows from the theorem of Brown, which stated that the set of multiple zeta values where the entries are elements in 2 and 3 generates the whole space. And this, of course, if we take all multiple zeta values where the entries are greater or equal to 3, then in particular we also have all multiple zeta values with entries 2 and 3. Okay, so these are some subalgebras of the space of multiple zeta values. So now let's go to our Q series G. So they were defined by this sum here, where these polynomials were these Eulerian polynomials. And so these were defined for arbitrary indices, k1 to kr. And we saw that, for example, if we multiply two of them in depth 1, we get again a linear combination of them which looked similar to the Schaffer product, but we also had smaller terms here. And this was a consequence of this lemma here. So every time you multiply a sum like this, you will do this ordering thing, and then there you also have the cases where these m's are the same, and then you need to say what happens if I multiply two of these rational functions. And the statement was that the product of two of them is given by this plus and then these lower weight terms, and these coefficients, these lambdas, were given by these rational numbers. So this somehow gives the idea how we should define our diamond, because in the classical case, if they would satisfy just the Schaffer product, then we wouldn't have this extra term here, and then here you could read off the definition of the diamond, which says that the diamond of a letter zk1 with zk2 is just zk1 plus k2. But since we now have these extra terms, our diamond, which we will define now, will look something like this. So again, we will take the alphabet AZ, and on this, and also with Q, and on this we define the product diamond hat by this. So it's similar to the Schaffer product, but we also have these smaller terms here, which are exactly coming from this here. And then with this you can check that this product here is actually commutative and associative, because basically it comes from this calculation here. So we get a Q algebra, Q AZ, with the quasi-shuffle product attached to this diamond hat. And we also get that we could define, by using our lemma, or first one could define a truncated version of these m's, of these g's, sorry, by this, and then these would, using this lemma we could define, let's do it like this. So here we have our algebra of letters, and now we want to define for each m an algebra homomorphism to the space of Q series. And what we can do is we send the letter zk to pk qm over 1 minus qm to the k. And if you take this, so first you can check that this is an algebra homomorphism because of this lemma, because the definition is exactly such that this is an algebra homomorphism. And then you can see that the capital M, Fm, in our lemma here, so if you use these Fm here with these Eulerian polynomials, then this is exactly these truncated g's, but this also makes sense for in the case when m goes to infinity. So the statement is that we get an algebra homomorphism from this quasi-shuffle algebra defined by this diamond here to the space spanned by our Q series G, which we denote by capital G. So the statement is that actually this space is also a Q algebra, which follows from our lemma, and then this map G is an algebra homomorphism from this quasi-shuffle algebra to the space G. And in this case, we also have these subalgebras we had before with these even and greater or equal to 2. But in this case, it's not trivial. Well, it's not hard, but it's also not trivial like before. And the statement is that the space spanned by all g's where the entries are greater or equal to 2, this is a subalgebra, and the space where spanned by all even are a subalgebra. And the reason for this is, so we need to check that these spaces of letters are closed under this diamond. So meaning to show that this statement here is true, that this is a subalgebra of our space G. So this is the G. We need to check that if I start with two k's here, which are greater or equal to 2, then this will also be a linear combination of letters greater or equal to 2. So this part here is clear, and here I just need to check that the case j equals 1 vanishes, but this follows directly from the definition of these lambdas, because if both of them are greater or equal to 2, and this space G even is a subalgebra, because if both of them are even, you check that these Zj for J odd vanish, because these Bernoulli numbers vanish if the index is odd. Okay, so these were examples for the most important examples for us. So we basically have now 3 examples of quasi-shuffle products we are interested in. So the usual shuffle, where this diamond is just the zero product, then the classical Staffel product, and also this this diamond head, which gives us the quasi-shuffle product for our Q series G. And now we want to prove some some identities in which are true for all quasi-shuffle algebras. And for this we will deal with some power series where the coefficients in our algebras. And this might get a little bit confusing because now we will deal with a lot of different products. But first some notation. So let's assume I have a power series with coefficients in our base field K. So this is F, and it's just a formal power series in the variable T with coefficients Cn. And now this bullet could be either the diamond product or it could be the quasi-shuffle product. And then we define for an element in A, so for a letter, we define what we mean by F bullet AX. So we plug AX into this power series here, so we replace this T by AX, and this bullet tells us what we should do with the A, because we plug this AX into this T to the N, so we need to say what we mean by A to the N, because there are different products we could use for a letter. And this could be either the diamond product, so we could just take diamond of A diamond, and so on. Or we could use the quasi-shuffle product, because elements in the space A, letters, are also words. This also makes sense to multiply letters by using this quasi-shuffle product. So this gives us a formal power series where the coefficients now in our space of words. Of course, if we take for the bullet the diamond, then the coefficients are in also in Ka, but Ka of course is a subspace of the space of words. And also what we could do, so if I have an element Z, which is now also a power series with coefficients in letters, then F bullet of this thing also makes sense, because if I have a power series, I could also plug it in here and then take the nth power, and this bullet just tells me how to evaluate these coefficients here. And also maybe one comment that these x are just the variables here, so they commute with these coefficients, but the coefficients here are usually non-commutative because they are elements in this thing here. And also every time we deal with elements in this power series here with coefficients in this space here, then we usually, if we multiply two of them, we will usually use the usual non-commutative multiplication in this polynomial ring here. So, and now with this we will give this general statement here, which is quite useful for, so this works for arbitrary quasi-shuffle algebras, and the statement might be at the beginning a little bit confusing because of all these different products, but the statement is, if we start with some power series where the coefficients are letters, then we have that the exponential with respect to the quasi-shuffle product of the logarithm with respect to the diamond product of 1 plus this zx equals 1 over 1 minus zx. And here, as I said, so this, if we view it as an element here, so what this basically just means is that we multiply it by using the usual non-commutative product in this polynomial ring. So this is just 1 plus zx plus zx squared. So here this is now the product in this polynomial ring plus zx cubed and so on. So these are words in the letters. If z is just a letter, then these are words in the letter z. But if z is a power series like here, we just multiply these two power series by using the non-commutative product. And here, so to evaluate the left-hand side, we first evaluate this log here. So we plug this zx into the power series, which is defined by this logarithm, and then with the powers of z will be evaluated by the diamond product. So this thing here is an element in Kax, and this we can plug into this in the exponential power series, where we evaluate the coefficients by using the quasi-shuffle product. Okay, and the proof of this we will do next time when considering linear maps induced by power series, and then we will prove a more general statement, but the implication will be this. But this we now want to use. So first, so let's say we have a quasi-shuffle algebra. So let's say, maybe let's do it more general. So we have Ka with the quasi-shuffle product. And now let's say I have some K algebra R, and I have an algebra homomorphism from my quasi-shuffle algebra into this K algebra R. Then, if I apply this algebra homomorphism to this equation here, then because here this is the exponential where I evaluate the coefficients by using the quasi-shuffle algebra, this will give me the usual exponential on this space R. So in other words, I get this. So if this is an algebra homomorphism, then we get this statement here that I can apply this phi to this thing here. And here, the right-hand side, I just apply phi to each term here. So now in this case, I choose this just to be one letter A. So here I have phi of A. And here I have now phi, so this is the exponential in R, and inside I have phi of this logarithm with respect to the diamond product. So here I have phi of A diamond, and so on. So this will be phi of just a linear combination of letters. So here this is really, if you say the depth of some object is the number of letters, so this is something in depth 1, and this is something in depth n. So in particular, this shows that this element here, phi a, can be written as a polynomial in these phi a. So this is in the polynomial ring phi let's say it like this, phi, yeah, let's say j, where j is just some letter. So what does this mean for our real objects? So for example, in the case of multiple zeta values, so let's say we have the Schaffer product, then, and let's say A is zk, well, what is A diamond n? Well, this just means zk diamond zk diamond zk diamond n times, but if the diamond is just the usual diamond for the Schaffer product, then this just means that this is znk. So here we would have phi of znk, and here we just have phi of a. And the consequence of this is that we get the following statement. So if we take as an example for an algebra homomorphism our truncated zetas, or just the multiple zeta values, then we see that the zetas of k can be written as polynomials in zeta in depth 1. So in particular, so this makes sense for all k's, because this is now the truncated version, but if the k's are greater or equal to 2, we can also take the limit n goes to infinity, and then this statement makes sense without these m's. So we see that zeta, for example, zeta 2 is a polynomial. So here the coefficient would be zeta 2, and here I have just even zetas. So this says that zeta 2 is a polynomial in zeta 2j. But this we already saw before, because these are just powers of pi, and this is also just a rational multiple power of pi. But this statement also, because this works here for arbitrary quasi-shuffle algebras, this also works for our small g's. And in particular, so if we take as an algebra homomorphism our small g, then here we have g of k, and the statement is that this is also a polynomial in these single g's, which were the Fourier expansion of classical Eisenstein series. Yes. So now let's do some more application of this. So here we saw that, for example, zeta 2 is a polynomial in even zetas, and this space is actually the same as the space of polynomial ring in pi squared. And you might ask, in this G setup, what is the correct analog of this space here? And this is what is called the quasi-modular forms. So again, we saw before that zeta, not just 2, but zeta of 2m, and so on, is always a polynomial in even zetas. But we also know by Euler that even zetas are always polynomials in zeta 2, because they are all polynomials in pi squared. So they are all in this ring here. And the explicit formula which you prove in your homework is this formula, and also this formula we saw before. And they are also explicit formulas for these as explicit rational coefficients times pi, times the power of pi. And we now want to talk about the analog of this space here, which is given by this. So the analog, the analog for these functions is g. And this is what we will call the ring of quasi-modular forms. And the definition is that this is a polynomial ring in G2, G4 and G6. So maybe a naive idea to find the analog of this space here would be just to say it's a polynomial ring in G2. But it turns out that this is actually not enough, and you really need to include G2, G4 and G6. And also, if you remember the space of modular forms, which we denoted by M, this was given by the polynomial ring in Eisenstein series G4 and G6. And one can also show that the space of modular forms, which just have rational coefficients, is exactly this ring here, where we choose G4 and G6 and take as coefficients Q. And you somehow see that this is this ring here, but we also include G2. And there are several motivations for this. And one motivation, for example, is what we will see also later in the homework, that this space is closed under QDDQ. And QDDQ in this space of modular forms, well, this is not closed, but this corresponds to the derivative up to some power of pi with respect to the complex variable tau. And the space of modular forms, which are holomorphic functions in the upper half plane in the variable tau, holomorphic functions, you can take the derivative, but it turns out that the space of modular forms is not closed under this derivative, and what you need to include is also the Eisenstein series of weight 2. So somehow you can think of this ring to be the ring which contains the space of modular forms, which is not closed under this derivative, but this is somehow the smallest space which contains the space of modular forms and which is actually closed under this operator. But in our picture now, you should think of this as being the analog of the space of rational multiples of even powers of pi, because we have this nice statement here, namely that all g's in depth 1 of even weight are actually in the space of quasi-modular forms. And this is the analog of the statement that the even zeta values are all in Q pi squared. But here we need to include G2, G4 and G6 and not just G2. And one example you already did in, or you will do in the homework, because there you showed that G8 actually can be written like this. So actually in the homework you show that E4 squared, which was some normalized Eisenstein series, is just E8. And this is equivalent to showing this equality here actually, that this small G8 is just this small G4 squared up with some factor and plus some multiple of G4. And this is of course an element in the space of quasi-modular forms. So this analog we have here, and this statement we will prove later in section 5 by using generating series and also some more generalized Schaffer product. But one consequence of this is, if we go back to this statement here, so we saw that G k k k k k is a polynomial in single g's, and also, which I didn't mention yet, but this g's, if they are all even, one can show that this is a polynomial in just single g's which are even. And by the statement we just saw, this is an element in the space of quasi-modular forms. So in other words, we have this statement here, that these G to M to M to M and so far and so far and so on are quasi-modular forms, which again is an analog of the statement that this is in Q pi squared. And also here you see that this equation can be seen as an analog of that zeta 8 equals 6 over 7 times zeta 4 squared. Because this follows from this by multiplying with 1 minus q to the 8 and then sending q to 1. Okay, so, and then at the end I want to mention this proposition here, which is homework. Namely, one thing I mentioned, that this space of quasi-modular forms is actually closed under this derivative. So for this you just need to say what happens if you take the derivative of G2, G4 and G6, and then using Leibniz rule you can conclude that the whole ring is closed under this operator. And for this you need to use this Schaffer product formula we proved for these small g. So if you remember, the product of two small g was given by the Schaffer product formula plus some extra terms, and these extra terms they included these derivatives. And then with this you can also show that the ring of quasi-modular forms can be written like this. So instead of taking G4 and G6 you can also take the first derivative and the second derivative of G2. And then here if I have an index where all entries are even, I can define what I denote here by G-sim of this index, which is just taking the sum over all possible permutations of these indices of this G. And you can then show, using this quasi-shuffle product we introduced today, that this is also an element in the space of quasi-modular forms. And even more, you can show that the space of quasi-modular forms is actually generated as a Q-vector space by these G-sims. And for this you just need to consider what happens if I take products of G2, G4 and G6, and using quasi-shuffle product you can see that you can always write them in terms of these G-sims. Okay, that's all for today. So next time we will talk more on quasi-shuffle algebras and then also talk about regularizations. See you then.